So for the last bit of this lecture, I want to switch tack a little bit and talk about multi-messenger astronomy. And this is actually an area in which I work. So I'm an astronomer by trade, and I've worked quite extensively on multi-messenger astronomy over the course of the last few years. And this is really doing astronomy with the aid of gravitational waves. So it's not a particularly relativistic subject, but I think it is a current subject which adds quite a lot of insight to what you can learn from general relativity, especially when you pair it with something that you understand quite well, like mainstream astronomy. And so the thing that's worth remembering about astronomy is that astronomy is fundamentally not a tactile subject. And what that means is you can't go out and get your sample and manipulate it in the same way that you could in chemistry or solid state physics or biology. You have to basically count photons in an array of increasingly sophisticated ways. That's what astronomy in general is. And of course, for most of human history, that astronomy has been done using the human eyeball as your detector. So it's not such a sophisticated way of counting photons. And then in the 20th century, there was a real revolution in our understanding of the sky by realizing, partly by accident, that in fact many astrophysical sources emit light across the electromagnetic spectrum. And so most things like stars and planets have a temperature. They emit light because of that temperature that they have. And therefore, they emit light somewhere between the UV and the infrared, and not much outside that. But there are also a range of other physical processes which allow you to see the universe across the electromagnetic spectrum. For example, some places in the universe have dust, which is very cool and emits in the far infrared. Some places have neutron stars that are very hot and emit in the X-rays. There are also a range of what we will call non-thermal emission processes, like synchrotron radiation, where you set up shocks and therefore can generate electromagnetic emission across the electromagnetic spectrum. And so by doing this multi-wavelength approach, you discover things like gamma ray bursts or pulsars or the cosmic microwave background or supermassive black holes. And that in turn gives you a much more complete view of the universe. And the hope, at the moment it is a hope, rather than necessarily a fully realized promise, is that multi-messenger astronomy will do a similar thing in the 21st century. And that is that if you pair electromagnetic light with some additional messenger, like a neutrino or a cosmic ray or a gravitational wave source, then you gain a much more complete physical picture of what is going on. And so what we have here is a diagram that sort of shows the frequency or the energy of a messenger. So on the far left-hand side, you have messengers which essentially oscillate once per Hubble time. And on the right-hand side, you have things with extreme energy. So the highest energy cosmic rays have about the energy of a well-hit tennis ball, despite the fact that they are only protons mostly on some heavier nuclei. So there is essentially a macroscopic energy. And the hope is that there are some extreme systems, like the binary neutron star merger that I show in this diagram, which actually do everything. That is to say, they make gravitational waves at detectable levels, they accelerate cosmic rays, they make neutrinos, and they emit light spectrum. And there's good reasons to expect that might be true. For example, here you have an artist's impression of a neutron star merger, but it's somewhat accurate, at least we think. And so you have some material which is thrown off in tidal tails, that is hot, it emits optical and infrared light. You have jets of light, or jets of matter created near the speed of light. They interact with each other and with the medium around to make shocks. Those shocks create synchrotron radiation across the electromagnetic spectrum, as well as producing the conditions to accelerate ultra-high energy cosmic rays and make neutrinos. And then critically, these are compact stars moving close to the speed of light at high frequencies, and they may well generate you detectable gravitational waves with frequencies of several hundred to a kilohertz or so. Of course, you may also have other things like supermassive black holes that merge, and they will merge at a much lower frequency. And so really that's the promise, if you like, of gravitational wave astronomy. Of gravitational wave astronomy in multi-messenger astronomy. And so what happens in the merger? Well, the merger is actually, potentially quite a complicated thing, but it does come down, for a period which is quite simple. And so firstly, making a binary neutron star is a singularly non-trivial thing to do. There's quite a lot of complicated stellar evolution that goes into making a binary neutron star. So that's singularly difficult, and it's also quite poorly understood. The actual merger itself depends on things like the equation of state of the neutron star and the relative masses and lots of messy physics that we don't understand so well. The remarkable thing is actually that the bit you understand, despite general relativity being very hard, is the inspiral. So having made two neutron stars, I can write this rather simple formula here, which tells me how long they take to merge. So 10 to the 8 years times a over the separation to the fourth power times basically the cube, 1 over the cube of the masses. And so, the things to note here, this is very sensitive on the masses, so much more massive systems merge much more quickly, and even more sensitive on the separation. And so a small range of initial separations can give you a huge range of merger times. And so there's a big astrophysical job going on to simulate the formations of these things and work out, for example, what the delay time distribution is. So how long it takes you from when you make your neutron stars to when you get your mergers, because that affects, for example, how common these events will be for gravitational wave detectors. Because if it turns out that all of them are made with separations of, say, 10 solar radii, right, then this number, this 10 to the 8, goes up by a factor of 10 to the 4, and it becomes 10 to the 12 years. And the universe is only 10 to the 10 years old. So if these are all born with large separations, and we don't expect to observe many because they don't merge in the age of the universe. If this number turns out to be quite small, you may expect to observe a very large number. So there's a big astrophysical effort to do that. But it's actually, this particular phase is perhaps one of the best understood phases. And then you get into the actual merger process. And then you can really start looking in a bit more detail at all the possible signatures that you might get in electromagnetic and gravitational wave light. So in particular, as the event is spiraling in, you get what's called the GW chirp signal. And so what's happening here is that the thing system is spiraling in and in and in and in and in, and the frequency is getting higher and the amplitude is getting higher, and eventually, of course, they collide, and then the frequencies, you get what's called a ring down, but in general, the amplitudes drop off quite quickly at the moment of coalescence. And although there's a possibility of some precursor electromagnetic emission, in general, the electromagnetic emission happens after that point. And then you might get, for example, a short burst of gamma rays. You might get what's called the afterglow, which is where the gamma ray jets plow into the interstellar medium. You might get then for various kinds of remnant. And so what you're getting physically when you have these mergers is that because these two neutron stars, of course, have a lot of angular momentum, not all of the material can end up in that central object that you form, be that either a black hole, which is the BH here, or the neutron star, which is the NS. And so instead you get an accretion disk, a disk of material spinning rapidly around it. That creates a lot of energy as it accretes onto either the black hole or the neutron star. It can power a jet of material, which is what gives you the short GRB. What it also does is it creates a huge number of free neutrons. Neutron stars are made up of neutrons, as the name suggests, and therefore they're actually very powerful places to make some of the very heavy elements in nature. And I'll get on to that in a little bit more detail later. But these are in general the signatures that you might expect to see. And so some of the key astrophysical issues that you might get at from this. So one of them is, do mergers create detectable electromagnetic emission? What is the origin of the heavy elements? So what we call the R process elements, and I'll get onto that in a minute. What's the nature of the short duration gamma ray bursts? Can we measure cosmology? Can we do the neutron star equation of state? Can we do tests of quantum gravity? And so a simple test that you can do, for example, is if you see gravitational waves under electromagnetic light, they've obviously travelled over some long distance from there to us, so you can check, does the speed of gravity equal the speed of light? And that's one sort of very powerful tool that you can use. So, what can you do? Well, to start with, you can do searches for the counterparts of black hole mergers. These are systems which are hard to find. We don't necessarily expect to see counterparts here, because if you have two black holes which are merging, as we've already seen, black holes have no hair. They're determined just by their mass, their spin, their charge. If there's no other material around them, you would expect these to be what you call electromagnetically quiet. You wouldn't see any EM light from them. The second challenge you have is that they're very poorly localized on the sky, and therefore it's very tough to actually pinpoint where they are. And so this is basically an effect of the fact that you have these two detectors, occasionally three detectors. And so if you have these two detectors, you just get an annulus on the sky, and you can use a little bit of polarization information to improve that, but it's quite hard. And what that means is when you've got a very large error box to search, you actually find many, many unrelated variable events. So what we call transients. So a transient is basically if you tile the sky repeatedly and you blink your images, transients are the things that change. And in particular, the things that appear and then vanish again on some time scale, which might be from minutes to years. And that's different from variables, which go up and down in some more consistent way. That said, there was a suggestion for this very first event that there was a counterpart, and this is a gamma ray light curve. This is from a gamma ray satellite called Fermi. So you see the background here, and you see this little faint flash of gamma rays from this first binary black hole merger here. This was suggested as an association. It remains extremely controversial, I think it would be fair to say, in the field. And I think that just shows, in a sense, when you're doing state-of-the-art research at the edge, things are not as settled as you might think, and things almost inevitably are digging into the noise to search for signatures. There are also other counterparts that you do find in the error boxes of gravitational wave sources. So this is an event called GW170104, so the 4th of January 2017. The error box from the error contours from the gravitational waves are in the back in pink here, and then there's some tiles from an optical telescope over the top. Interestingly, this particular event, Atlas 17 AEU, was found inside the error box. It was a fast fading transient. It wasn't there a few days before. There was quite a lot of excitement. It turns out it's actually a gamma ray burst afterglow, but it's a gamma ray burst that wasn't related to the gravitational wave source. And that's quite unlikely, but it turns out the distance is just too large to explain that. And so it really does look as though this is an example of an event which was serendipitously found. And when you have a very large error box, you find these unusual things when you look very carefully. So, the black hole searches have been quite extensive, but they in general have not been successful. And so that brings me on to this event, GW170817, and associated with GRB 170817A. And so what we see here at the bottom, and on the right-hand side, this is the gravitational wave chirp signal. This is the gravitational wave chirp signal. It actually lasts for about a minute, and only the last 10 seconds are shown here. And you see it sweeping through the frequency as the binary neutron star gets closer and closer and closer until it eventually merges. And you see it here in the three detectors in LIGO Hanford, in LIGO Livingston and Virgo. It's very clear in Livingston. It's fairly clear in Hanford. It's not actually there in Virgo, but that tells you something important as well that we'll get onto in a minute. And then in the left-hand panel here, this is the gamma ray light curves again. So time versus brightness, this time from Fermi and from something called integral. At about 2 seconds after the merger, you see this faint flash of gamma rays seen in both these two different instruments, which really confirms this time it's real. And in fact, this gamma ray burst was identified before the announcement of the gravitational wave source. So these GRBs, short duration GRBs, happen at a rate of a few per week. So the probability of getting one within 2 seconds of the very first binary neutron star merger that you see is extremely small and already suggestive of an association. But then you need to narrow down where they are on the sky. And so you can do that in a few ways. So, the Fermi telescope itself provides a position. You can also use the time delay between the two satellites, because they're obviously in different places, as a guideline to give you an annulus on the sky. And then you can narrow down with LIGO and Virgo what you're seeing. And so LIGO itself gives you this light green area, And I just mentioned a minute ago that Virgo didn't see anything, and you might think, well, how come if Virgo didn't see anything, when I use Virgo I get this dark green area which is so much better? And the answer is that the gravitational wave detectors have what you think of as an antenna pattern. So they have regions of high and low sensitivity on the sky. And the fact that you didn't see it tells you that it must have been in a region of low sensitivity for Virgo, and therefore it basically breaks the degeneracy between the top and the bottom bits of the LIGO error box and places it firmly in this upper region here. And this is a region about 30 square degrees across, or of order 100 full moons or something like that. That's still hard when you think of the fact that most big telescopes have regions, fields of view which are a fraction of a full moon. Still hard, but it's nonetheless possible. And the gravitational waves are also very usefully, because you actually measure the masses of the components from the waveform, from the in-spiral. You actually get the masses. That tells you how bright or how large the strain was at the source, and it therefore enables you to use the measured strain to infer a distance. It means that the gravitational wave mergers are what we call standard sirens. And those sirens allow us to measure a distance, and in this case it's about 40 megaparsecs. And so as night fell, in Chile in particular, the evening after this event had gone off, it was possible to know a patch of sky and a distance. My narration too much. Okay, so let's go back to this slide. So this is the error box that was available to be searched from Chile at the time of the sunset, essentially, in Chile on that first night. And there are a couple of different approaches that you could use to actually do this. And so I just mentioned that you get the distance. So one thing you can do is you can just go and hit all of the galaxies inside this error box individually. The other thing you can do is you can go and try and tile the entirety of this error box with a wide field telescope, or you can do some kind of hybrid. And so these are three different approaches. So this is the SWOPE approach. They were the first to identify a counterpart. I was involved in this effort with VISTA and the VLT, and then there's this effort from DECCAM as well. And what several different groups, in fact 6 different groups independently did, was point at this galaxy, NGC 4993, and this is an image on the left from the Hubble Space Telescope in April 2017. This is the image of August 17th, and you see this little dot which appears at the end of the arrow here, which wasn't there in April. This is a new source which appeared in this galaxy, which is at the right distance, and has a series of observations having identified it. And this image on the right here just shows you essentially all, the time scale in logarithmic time, all different observations in the different wavelengths. So an incredibly intense set of observations that were taken of this particular event. This is just an image there of the host galaxy here, and so the event is sitting just to the top left of the centre of the galaxy, and if you look at the right-hand panels, you can see how it started very blue and then became very red. So the top panel is an image from a pre-image, so an image taken from the VISTA telescope before this event, and then you have these images lower down where you can see this transition from blue to red. And what we're actually seeing here is emission from a so-called kilonova. And I mentioned earlier the idea of the synthesis of very heavy elements. And I mentioned something called the R process. And so now it's worth explaining what I mean when I talk about that. So if you think about how you create elements, you create some of them in the Big Bang, the hydrogen and the helium, and a tiny bit of the lithium you create in the Big Bang. Then you start doing nuclear fusion in the cores of stars. And nuclear fusion is successful at building things all the way up to iron, which is at the peak of the binding energy per nucleon curve. So in stars, you can't build things that are heavier than iron through fusion, because it's just not energetically favourable. And in fact, in stars, if you evolve stars and you make an iron core, then you stop making energy, and that's when they explode as supernovae. So you can't easily make heavier elements than iron, and yet they exist in nature. And so you can ask yourself, well, how does that work? And the process that it works through is something called neutron captures. And here, a neutron capture is if you take some seed nucleus and you bombard it with neutrons, and it captures those neutrons, it becomes a heavier isotope of the same element, but it can progressively captures more and more neutrons until eventually it becomes too heavy to be stable, and then it decays. If it goes through a beta decay and therefore gives off an electron, it eventually gains a proton in its core and therefore moves up the periodic table. And there are two forms of neutron capture. So one where the neutron capture is slow, and what that means is that as soon as you create an unstable element, that element decays before you can capture another neutron. Or you can have neutron captures which are rapid, the R process, where you bombard it so quickly that it doesn't have time to decay, and you can build even more heavy elements in that way. And although we know where the slow process works, we have not known where the R process happens in nature really until quite recently, more or less until now. And so neutron stars are a very promising place to do this because, of course, when you merge two neutron stars, you throw some material off because of the tides, and that material, therefore, is very neutron rich and it bombards whatever's around. And so it's been long suspected that you should make heavy elements in neutron star mergers. And the hallmark of that is that if you make very heavy elements, in particular if you make lanthanides, which are at the very bottom of the periodic table, if you can remember back to your chemistry, elements have a shell structure, so SPDF, and most elements do not have F shells. On the other hand, the lanthanides have open F shells. They have electrons in F shells and lots of free energy levels to hit. They're the outer F shells, they're very complex, and so there's a myriad of transitions. And what that means is if I shine light at a gas made of lanthanides, it will just get absorbed by some atomic transition, because there's always an atomic transition at almost every wavelength. And that means it will just gradually heat up and emit infrared light at some later stage. So the prediction of the models, if heavy elements were being synthesized in these systems, is that you should get early blue emission followed by later red emission, because you synthesize these lanthanides and so you get a peak that's red later. And so this on the left hand side here is the light curve, that's just brightness versus time. In the blue here we have blue but visible light, and in the red we have what's called the K band, that's infrared light, and you see the K band is brighter and lasts much longer than the blue. And that's just backed up here in the spectrum. So the spectrum shows you wavelength versus brightness, and then the times here, the 1.5, 2.5, that's just the time in days since the merger, and you see this early blue bump which fades rapidly away, and the infrared bump that rises. And so this looks very much like you expect from the synthesis of these elements in what's called a kilonova. And that's not all you saw, so I've already mentioned the idea of multi-wavelength astronomy, and that non-thermal emissions, so shocks and synchrotron radiation, generate material across the electromagnetic spectrum. And indeed, in this case, if you looked deeply in X-rays and in radio light, you actually saw this event in radio and X-rays, which told you that it's generating an afterglow, where you've got material ejected at relativistic speeds, which is ploughing into whatever's around it and setting up shocks. And indeed, this afterglow is consistent with the properties of not material which is ejected at relativistic velocities in all directions, but is ejected at relativistic velocities in a narrowly confined jet, and we're viewing at something like 30 degrees to that jet when we see it. And indeed, you can test that. And so again, earlier in the course, I mentioned the idea of very long baseline interferometry when I talked about the Event Horizon Telescope. So the idea being that if you want to have sufficient resolution to measure the event horizon of a black hole, you need a telescope the size of the Earth. Well, you can do many other things with telescopes that are the size of the Earth. And one of them is that you can get very high resolution images, not quite as high a resolution as the EHT images, but still very high resolution. And what you see here is two different approaches to this. And so in one here, you can actually see that the position of this radio emission is moving with time. And in the other, you can kind of also see the same thing, that you actually have a structure here which is moving and elongated. And what that's telling you fundamentally is that you have a jet of material that's creating this, and it's actually moving through the interstellar medium of that galaxy at basically the speed of light. You know, it's got a Lorentz factor of several at least. And therefore, it is a direct test of the idea that you make a relativistic jet in these mergers. And so when you put all of that together, this is what you get. It looks fairly impressive, and this tells you exactly what we're seeing in this merger. It's the first time we've been able to put something like this together with anywhere near this level of sophistication and cleverness. And so what you have is a newly formed object at the middle here, probably a black hole, although there is still a suggestion it may have been a neutron star, even if only for 100 milliseconds or so. You make an accretion disk around it. You have neutrinos which come off your accretion disk. These effectively alter the neutron richness of material around the disk and make what's called the blue kilonova, where you make R process elements, so some heavy elements like xenon. In the tidal tails, you throw off very, very neutron-rich material, and you make what's called the heavy R process elements, so gold and uranium and things like that. That's the kilonova, which is responsible for most of the optical and the infrared light. You also have this GRB jet here, which is very powerful if you look straight down its axis. We didn't look down its axis in this particular occasion because we were looking at about 30 degrees or 20 to 30 degrees off it. And so that combination of gravitational waves plus light allows you to build this sort of picture for the very first time, and therefore do a great deal of quite impressive deconstruction, if you like, of what's going on in terms of the actual physics of these extreme events.